Hi, welcome to Module 1, the first module of Lecture 16. This is the last module of Part 5 of the course, which is the last part of the course. So you've reached the end here of the course. So the topic of this lecture is a little more specialized than the previous two lectures. And again, it falls in the category of can be safely skipped the first time through. The topic, though, is an important one, particularly in game theory. It's Optima, comparative statics, and implicit differentiation. And the idea conceptually is a straightforward one that you've sort of seen before. When you optimize a function, usually find the maximum, you create you obtain some maximum, right, for each of the variables. Right? So, for instance, you might obtain, the maximum over here, or it might be a vector, like we did in the previous. So this is part 2 of the class. This is part 5 of the class. We obtain different maxima. And usually there, we didn't have any parameters. We just found the maxima in terms of numbers and stated the maxima was 2 or 5 halves or whatever. In practice, though, what we want to do is we want to parameterize our models to take into account parameters and factors that happen in the real world. So, for instance, in the previous lecture, we optimized under the constraint of a budget, under a budget constraint. There we just put numbers in for the budget, but what if we wanted to understand more generally how the changes in the budget affected the outcome of your optimization choice? Well, that would be a parameter of the model. When you have a parameter of the model, then the optimum itself becomes a function. So if the parameter is alpha, or alpha over here, here's a single parameter. Then if there's a parameter in your maximization problem, right? If there's a parameter in the objective function you're trying to maximize, then that parameter will end up in your optimum itself. And I'll show you an example of how that works in a second, but I just want to talk a little bit conceptually about what this is first. So when you find an optimum, when you find the maximum of your utility, for instance, you will often have that maximum itself be a function of existing parameters. One parameter might be the budget constraint you're under. Another parameter might be the cost of this action or that action, right? Now, why is it important? Well, oftentimes, particularly in game theory, we do not actually believe that our optima themselves are set in stone, right? We don't believe that individuals will always do exactly this or exactly that, right? It's difficult to say that. That's a very strong claim. It's a point prediction. Effectively, you're predicting an exact action of an individual. That's a difficult claim to support. However, we do tend to believe that the way in which these point predictions, these equilibria, change with respect to the parameters is somehow reflecting aspects of the real world, right? So if my equilibrium action decreases as the cost of that action increases, as we would usually expect, we tend to believe that actually is true, right? We tend to believe that actually is representative of what's happening in the real world. When costs increase, we do expect people to do the action associated with that cost less frequently. So we do tend to believe the way our equilibrium action changes with parameters. Understanding how our equilibrium action changes with parameters is known as comparative statics. Now, this is a pretty weird term because you're comparing things that are static. Well, here's what it means. An equilibrium of a game, for instance, is a static entity. An equilibrium set of actions is a set of actions from which no individual has incentive to deviate to different actions. Therefore, if everyone is playing their equilibrium actions, his or her equilibrium actions, then no one will have an incentive to change, and therefore everyone will stay there. So an equilibrium is a static point, right? It's like a steady state in the case of a dynamic process. Incidentally, dynamic processes work the same way here if you're trying to analyze steady states. So you're trying to look at a static process, right? A static situation in which everyone is playing equilibrium without changing. However, you want to compare the nature of these static states, of these equilibria, across different values of the parameters. And that is a comparative static. You're comparing an equilibrium across different values of the parameters, right? And that's what we most care about oftentimes in game theory. Not always, mind you. Sometimes we do care about the actual equilibrium prediction. Often we do. But we also care often more about the comparative statics of our model. In particular, the ways in which our equilibrium actions vary with the parameters of the model. I should say this is not just constrained to game theory, even though that's the example you'll see most often this used. As I said, it can be used for any analysis of, say, a dynamic process in which the process is a function of parameters. You can also look at how things like the steady state of a Markov process varies with parameters. It's also sometimes used for statistics. If your estimators depend on some parameters, you can employ sensitivity analysis to see how the estimator varies with the parameters. In general, this is a very general concept in which you are looking at how a particular outcome of some process, be it an equilibrium or a steady state of a dynamic process or an estimator, right? You're looking at how some object that you've discovered or found or postulated or whatever, some object varies with some exogenous parameters. Note these parameters must be exogenous. They can't be endogenous because endogenous factors don't end up in the final outcome of these processes. The equilibrium itself is the solution of what should happen in equilibrium for those endogenous variables. What you're looking for in comparative statics is how these endogenous factors, these choice variables that you've solved for at equilibrium, vary with exogenous parameters. Okay. How they vary with endogenous variables tells you more about how the strategic interaction of the game works, so sort of the internal logic of the game, but it's not a comparative static. It's not telling you about the how the equilibrium varies with exogenous parameters. Okay, so that's the sort of setup for why we're doing this. Now, there are sort of two ways this can come up. The easiest way is what we're going to talk about in this module, which is when you have an explicitly defined function. So the examples up here, I just gave x star of alpha or x star vector of alpha. These are explicitly defined optima, right? We obtained them by solving the optimization problem, and then in this case, and then writing down the optimum x, the optimum value of x, as a function of some parameter. These are explicit functions. They are defined explicitly. We're going to say this equals something, or this equals something. Right? This could equal, I don't know, 3 alpha squared minus 1. This might equal a vector alpha plus 1 e to the alpha. Right? Either way, they are just functions of the parameter alpha, and they're explicitly defined functions of that parameter. This will turn out to be helpful for us, but let's back up for 1 second and show how you get these things. There's a slightly more complicated example in the book. Let's do a simpler example. Let's say you have some function similar to what I had before. Let's get rid of the y variable. Before by me, I mean the last lecture. Let's say we want to maximize this function. We did it before, right? And we said that the maximum of this function was 3 minus 2x equals 0 is the first order condition. That implies x equals 3 halves, right? Now again, if that was way too fast, you should not continue on in this video. You should go back and revisit either one-dimensional calculus or multivariable calculus. The stuff from this one is, as is true for the past 3 lectures, requires a good understanding of previous material in the previous lectures and previous parts of the course, particularly parts 2 and parts 4. Okay, so that said again, the maximum of this function, one dimension is 3 halves. But what if we have some parameters associated with this? Let's say we have some c over here. What would that c be? Well, it might be the cost, right? Right now we assume this is sort of a situation in which you want to produce something, and you get a benefit equal to 3x, and there's a cost x squared, so the cost is increasing. But what if we had some parameter on the cost? So we could vary the exact cost. What would happen then? Well, the first order condition would be 3 minus 2cx equals to 0. that would imply that x star equals 3 over 2c. You see it matches the previous answer. When c equals 1, you get 3/2. But we can do more with this thing, right? Because now we understand, we now explicitly have the optimum over here is a function of the cost c. So by incorporating parameters into our objective function, what we've done is enabled our optimum to be a function of these parameters. In this case, it's one parameter. What if we get rid of the 3 and change it to, well, make it b. bx minus cx squared. So now b is sort of like a benefit, a relative benefit. C is kind of like a cost. Again, we can do the first order condition, and we get b minus 2cx. And we discover x star equals 0, and we solve that and get that x star of b and c is equal to b over 2c. Now we have an explicit function of 2 parameters. And we can keep going with this and adding more parameters, but the point should be clear at this point. The optimum x star is a function of the parameters itself. So your optimum, where before was just a number, here is a function itself. And that is key conceptually, because the fact that the optimum is a function allows us to explain how our optimal choices vary with the parameters of the model. How do we do that? Well, that's most of the topic of this particular lecture. This is a very short lecture, by the way, 23 modules. In this module, we'll discuss very briefly how you do that when you have an explicitly defined function. This is an explicitly defined function. It's an explicitly defined function because, I'm just rewriting it here, because it is a function of 2 parameters, such that you can write the dependence on those parameters explicitly. Now, if you want to know how the optimum here, how the maximum changes with the parameters, how do we do that? Well, we use the fundamental thing that defines a change of a continuous function, which is a derivative. So we take the derivative, this is always the total derivative, the derivative of the function with respect to whatever parameter we care about. Let's do b first. What's this? Well, with respect to b, c is a constant, and c is not a function of b, so it's effectively constant. So we have just the derivative of b is 1, so this is just equal to 1 over 2c. Now what do we do with that? We again don't typically care about the actual form of the derivative. What we care about is its sign. Is its sign accurate or not? Well, if c is positive, then this thing is always positive for a finite c. So we learn that the optimum choice is increasing in the benefit, in b. That is entirely intuitive, right? That is usually not what a game theory paper would focus its core results on. Like, look, the benefit makes you do it more. Higher benefits make you do it more, right? That's true. That's a nice sanity check, though, to make sure you have the right, your model makes sense. But as an example, it works well because it shows that you can figure out how the optimum choice, x star, is increasing in the benefit b. The same thing with c, the cost, and you might guess that it should be decreasing. So we'll check that. What's here, b is a constant. The derivative of 1 over c is, remember the power rule is negative 1 over c squared. So you get that. For all finite values of b and c, that is negative. So this is less than 0. So as you might expect, as you increase the cost of taking some action, the action is taken less often in equilibrium. Again, entirely intuitive, but it's just a sanity check for your model. And this in a nutshell is how you do comparative statics for an explicitly defined function. You just take the derivative. Oftentimes, there'll just be a normal one-dimensional effective derivative. It might be the case that your parameters are functions of each other. So for instance, what if b was a function of c itself? Well, then you'd use the total derivative instead of, well, you'd still be using the total derivative, but now since b is a function of c, there's both a direct effect of c on x star, and also an indirect effect of c on x star. So this thing, if now b were a function of c, would look like that plus dx partial x star partial b db over dc. If you recall, this is the equation for the total derivative, and you have more than one dimension. This is the direct effect of c on x star, and this is the indirect effect of c on x star acting through b. So sometimes this is a more complicated derivative to define explicitly, but typically our parameters don't depend on other parameters. So typically we have derivatives look just like this when you have an explicit function, an explicitly defined optimum. And that's the core concept of this module, which is you can define an optimum as a function of its parameters, and then differentiate the optimum with respect to the parameters to tell you how the optimum changes with the parameters. These are comparative statics of your underlying model, and are usually what is of interest. And again, the same logic can be applied to sensitivity analysis in statistics, or looking at how steady states or whatever vary in dynamic systems. Okay. When you cannot define your optimum explicitly, then you have to use what's called implicit differentiation, which is the topic of the next two modules, the last two modules of this lecture. Before finishing this lecture, though, I want to mention briefly how this relates to the change of the function itself, not the optimum, but the objective function itself with respect to the parameters. Typically, we don't care. Typically, our interest is in how the optimum changes with parameters, but sometimes it can be helpful to understand how the objective function, say utility function, how the utility function changes with its parameters itself. So we'll talk about that very briefly with respect to the envelope theorem. Okay. So the envelope theorem, and again, I'm not sure why I'm saying envelope instead of envelope. I say normally envelope, but for some reason the word envelope theorem makes me feel weird. So the envelope theorem says basically this. Let's assume we have some function, some utility function or whatever other function. It's a function of an x, which is the variable, the choice variable, and some c, which is a parameter. And let's say that you're going to optimize this, which you would do by computing the first order condition and setting it equal to 0, which would give you some optimum function of c x star. This is just what we talked about before. Just what we just talked about. So what if instead of wanting to understand how x star changes with c, we want to understand how f changes with c at the optimum point x star? Well, if we want to understand how f changes with c evaluated at x equals x star, we can rewrite this thing as this, and then use the chain rule like we just did. So here we have the, I'll write the, so here's the direct term first, df, partial f, partial c, evaluated at x equals x star, plus, I'm sorry, my next line here, ran out of room, plus the indirect term, which is partial f, partial x, evaluated at x equals x star c, times dx star c dc. Now, first you might think, well, what's the point of that? But note, this thing is the partial derivative of f with respect to x, which when evaluated at x star must give you 0. That is the first order condition. So because of the first order condition, this thing is 0, implying this whole term is 0, implying this is the envelope theorem. The effect of the parameter c on the function itself, evaluated at the optimum point x star, is exactly equal to the partial derivative of f with respect to the parameter c evaluated at the optimum position. How does it help us? Well, I give an example in the book. I'll give a similar one now. Let's say you have some function that's, let's say, c to the third x squared minus c to the fifth. Well, you could go through and calculate x star if you wanted to, or you could calculate partial f partial c evaluated at x equals x star. What's that? That's going to be, and I'm going to put a plus here actually. That's going to be 3c squared. Then treat x as a constant, just evaluate it at x star. So this is x star c squared plus 4c to the fourth. How does that help us? Well, that's positive, that's positive. This has to be positive regardless of what it is because it's squared. So this thing is greater than 0. So I've just determined the sign of the rate of the change in the function f with respect to c without ever calculating the optimum. So in this case, we can use the envelope theorem to understand how the function itself changes with respect to the parameter without ever calculating the actual optimum. You can't always do that, but when you can, it can be helpful. And in general, knowing how the function itself changes with respect to the parameter can be a useful piece of information. We talked about it a little bit when we discussed the meaning of Lagrange multipliers in the previous lecture, which is sort of a special case of this. Okay, so that's mostly for this module. One thing I want to close on is comparative statics, besides being very useful for game theory, also are sort of centrally attached to the whole endeavor of EITM, which is movement in political science, stands for empirical implications of theoretical models. And the idea is to connect your theoretical model, your formal model, to empirics. How do you do that? Well, you often can't test if something is a particular point, right? If a person has a strategy that exactly follows some point prediction, but you can test the direction that that strategy changes with respect to some exogenous parameter. You measure the strategy, you measure the parameter, or proxies thereof, and you see if the direction of change, the direction of the effect of the parameter on the strategy is in the direction your theory predicts. To do that, you need comparative statics. So if I have some x star, which I can measure, it's a function of some parameter alpha. If I take this thing, and this ends up being positive, that's an empirical prediction. It says my object of interest, my strategy x star here, is increasing in the parameter. How do I go measure if that's true? Well, I could measure that x on the left-hand side, and I could say, via linear regression, say, looks like that. Here's my linear model. And my expectation is that beta 1 should be significant and positive, that alpha should have a positive effect on x. So that allows you to tie empirics, so your formal theoretical models to empirics, and comparative statics are central to that endeavor. So that's another reason why this is an important part. Okay. But that covers this. And whenever you have an explicitly defined an optimum, this is all you need to do. This is it. This is the entire topic. However, oftentimes the algebra is such that you cannot actually back out an explicitly defined optimum. Instead, your optimum is defined implicitly. And when that happens, you have to use techniques called implicit differentiation to get at your comparative statics. And that's the topic of the next two modules. Thank you very much.